Actually, the presentation this morning were very interesting, especially the discussion around the change of understanding of our information around frequency and penetrance, because there's a lot of things that are currently not really noticed, whether it's in terms of variant or in terms of disease, and I wanted to go over that. And I feel that over the last few years, or at least over the last year, the environment in genetics is changing incredibly rapidly. Last year we had release and the release and the publication of the first genome by the telomere to telomere consortium, and for that, there's been a lot of value from using ultra long read and moving toward using long read only on Nanopore to generate that genome. But much beyond that, and I was incredibly surprised when I live in the UK, when it was discussed on Radio 4 about a month ago, but it's the adoption more and more of things like the pangenome, and the fact that it's really going to the use of the first draft pangenome and those 47 genome on different population is going to really change, I think, and we think, the way genomic is going to be adopted in the clinic. And the fact that even those only 47 genome sequence are already showing that it's decreasing errors in detection of small variant by a third. It's also increasing the number of structural variants that are detected by haplotype. It's really different. Even the pesky Y chromosome is now completely sequenced end-to-end. I'm not going to read the quote because I expected to have a laptop there to be able to read it, and I can't read from there. But it's changing already the way people approach genomic in the clinic. And it's not just the reference genome that are changing and that are changing very quickly. There's been a lot of advance in treatment and actionability and the thing that we've been discussing. But the International Rare Disease Research Consortium is keeping track of the drugs or the orphan drugs that are being used. And there was, I think, 14 or 17 in 2010, and there's now almost 550. And this morning you heard there's about 770 or 780 rare diseases that are treatable. So that's changing very quickly. Things that are treatable today are most likely to be, things that are not treatable today are very likely to be treatable in the very near future. And it's setting up those projects, those experiments in a way that's flexible enough to be able to move with what is achieved. And the last but not least of things that are changing very quickly is what we're thinking in terms of variants that are that so far were hidden, and then now we can look and analyze. If you look at short-read sequencing, it does miss about 8% of the genome, and you could say it doesn't really matter. But out of those, 34% of the variant in the genome are made of, of mutation are made of variants that are more than one single nucleotide. And if you looked at the effect of those slightly larger variant and a structural variant, on average, they're about 30 times. They have about 30 times more effect on gene expression than a SNP. So if you're not looking at those, you might miss a very large effect on the phenotype. And last but not least, we haven't been talking about methylation so far this morning, and that's something I believe strongly that's going to be really important to understand disorder in general, but especially rare disorder. And the techniques that are used at the moment cover about 3% of the genome. So when are the technology going to be adopted that cover a lot more of that, to all the genome? So I want to switch gear a little bit, and I've got 3 examples of disorder where I think long read can really make a massive difference. The first one has been the poster child, I think, for long read for the last year or so, probably because there's treatment now. But there's treatment that needs to be done before apparition of symptom if you're looking at gene therapy. So you need to be able to test well, and you need to be able to test very quickly. And testing well that locus where, of course, you do have that homozygous deletion on SMN1, but because you can have that partial difference in functionality, that partial functionality in SMN2, and the fact it has an effect on the phenotype, you really want to have a really good understanding of the locus. And the slide here was very kindly provided to me by Danny Miller at Seattle University to show that first, the long read are covering really, really well. Danny works with us on a regular basis. And also that region is really rich in ALU and also very prone to structural variants. So to be able to understand what's going to go on in SMA and what the outcome is going to be, you really need to have haplotype long reads to really enable the identification of the structural rearrangement in that locus. The second one is, because it seems to be on everybody's mouth again, is Fragile X. So I'm not going to go in detail, but obviously you want to understand the repeat structure in FMR1. And now it's disrupted, but Fragile X is also the repeats involved in disruption in methylation. And again, that's where Nanopore long read is giving you a very clear understanding of the repeat region, just because the read by themselves cover the whole region. So you don't need to start doing complicated assembly. But it also gives you native methylation profile. So you do get everything in one test on that locus. And obviously, you do get it in a haplotype resolved manner to really understand the molecular presentation of those people. And I'm going to be brief. The last one was just because I found that example absolutely beautiful, because you've got a sea of red and a sea of blue. And it's an example of two prototypic disorder, Angelman and Prader-Willi, is the same promoter region. One is fully methylated, the other one is fully unmethylated. And as you can see on the slide here, you can really replace several complex and specialized assays to correctly delineate that region and the pathogenesis. And by that, I mean, of course, you're going to look at the methylation profile, but you can get all the other information around structural variant and rearrangement that might have an effect on the outcome. And newborn screening, and I know it depends really much on the different projects, but some of them seem to be doing proband only, and therefore one of the discussion is you don't have a phenotype, the kid's still fine, hopefully, and you're not planning on sequencing the parents. How are you going to be able to do all that prioritization and understanding what's really going on? And so that's not patient sample, that's a corneal sample that we did in the lab, but we can really show that we can haplotype resolve the allele from single sample, and we think that in the future, obviously it's going to help for newborn screening, but we also think it's going to reduce the barrier of adoption, even in rare disease. And I don't mean in rare disease in NICU-PICU, but I'm thinking in rare disease in adults where you don't necessarily have the parent, or the participant doesn't necessarily want to talk to their parent and ask for samples. And so really, we've really seen that what are people missing really matters. And there are now solutions with this where you can look at all the variation. You can look at those variation in a haplotype resolved manner, even if you do not have trios. And you can also look at all the modification. I think at the moment, it's mostly 5-HMC, especially in rare. But you do get 5-MC, but you also get 5-HMC, 5-MA, and more modification. And last but not least, and that's my more commercial slide for people who want to see, you know, is anybody really doing it? Doing those large projects with Nanopore, and we have beautiful example. We have a really nice project that we're working with Cora at the NIH on very large scale sequencing in Alzheimer's disease. Obviously, and Emma Baple is here. We are working with Vacher to start accelerating the deciphering the genome on very specific presentation, and we do have a project in Germany called Longer, and that's going to be over 3 years for the adoption of long read in rare disease for improving the diagnostic. Thank you very much.